Sample problem 3.11. Nitrous oxide, which is N2O, also known as laughing gas, is commonly used as an anesthetic in dentistry. It is manufactured by heating ammonium nitrate. The balanced equation is NH4NO3 solid is heated to form N2O gas plus 2H2O gas. In part A, we are asked to calculate the mass of ammonium nitrate that must be heated in order to produce 10.0 grams of nitrous oxide. And then in part B, we are asked to determine the corresponding mass of water produced in the reaction. Okay? So this is a mass calculation. We're going to take what we learned in the previous sections and put it all together here for this type of problem. So what I'm going to do is I'm going to write down the chemical formulas of all the substances that are in this compound, in this problem. And I'm going to go ahead and calculate their molar masses, because we'll need their molar masses for this. So nitrogen, notice there's two nitrogens here. So 2 times 14.01 grams. There's 4 hydrogens, so 4 times 1.01 grams. And then there are 3 oxygens, 3 times 16. So that's what? 28 and 48 and 4. So 28.02 plus 4.04 plus 48.00. And you get 80.06. So that's how much 1 mole of ammonium nitrate weighs. Let's do N2O, 2 nitrogens, and 1 oxygen. So that's 28.02. So 2 times 14.01 plus 16, 44.02. And then for water, 2 times 1.01 grams, plus 1 times 16, 18.02. Wouldn't be surprised if you already remembered that, because we do water quite a bit in these types of problems. So those are our molar masses. So let's do part A. Calculate the mass of ammonium nitrate that must be heated in order to produce 10 grams of nitrous oxide. Remember, the nitrous oxide is the N2O. So 10 grams of nitrous oxide N2O. Okay? Now, what we want to do is get this into moles. These types of problems, generally the first step is to convert it to moles. So N2O, to convert it to moles, we would say, look, it's 1 mole of N2O per 44.02 grams of N2O. That's why I did the molar masses at the beginning. So 10 divided by 44.02. And you get 0.2272. Okay? Now here's the logic this. They're asking us about ammonium nitrate. The relationship is, if you look at the balanced equation, it's 1 mole of N2O for every 1 mole of ammonium nitrate. Balanced equation. Or 1 mole of ammonium nitrate for every 1 mole of N2O, sorry. It's easy to say NO2, but it's N2O. Okay? So which one are we going to use? We know how much N2O we have. We already calculated it's 0.2272 moles. We want to know how many moles of ammonium nitrate are going to react to form that N2O. So the next step, we're going to pick this one here, because that one puts the ammonium nitrate in the numerator. So 0.2272 moles of N2O, and then it's 1 mole of ammonium nitrate per 1 mole of N2O. So that cancels. and that'll give you the moles. Well, obviously it's going to be 0.2272, right? Because if you multiply a number by 1 over 1, it's not going to change the value. So that's 0.2272 moles of ammonium nitrate. And then we just want to convert that to grams. Calculate the mass. So that's a mass conversion. We go from moles to grams, okay? So the ammonium nitrate's right here. There's our conversion factor. 80.06 grams is how much 1 mole weighs. So I'm going to take our 0.2272 moles of ammonium nitrate and then multiply that by 80.06 grams. There's not much room in here, but I'll try to fit it in. Divided by 1 mole of ammonium nitrate. All that's doing is converting it from moles to grams. So 0.2272 times 80.06, and it's 18.19. There you go. Okay, so let's go back over the logic here. We need to have the molar masses so that we can do these sorts of calculations. The reason we need the molar masses is because the conversion factor from one reactant to another or one product to another has to do with the number of moles. We can't convert directly from masses very easily, so we convert it into moles. So 10 grams of N2O is converted into moles of N2O. Then we look at the balanced equation and we see that there's 1 mole of ammonium nitrate produced for every mole of N2O. So taking that 0.2272 moles of N2O, multiplying it by that ratio, that gives you the moles of ammonium nitrate that would be reacting in this particular problem. Use its molar mass and convert that to grams and you've got your answer. Now, in part B, we want to determine the corresponding mass of water produced in the reaction. Now we want to know how much water is produced. What we know is how many moles of N2O are produced. We know that. That's right there. So I'm going to use that piece of information right there, and then I'm going to erase everything underneath because I can use that. We can use that piece of information. Okay. All right, here's how we can use that piece of information. Every time that you produce 1 mole of N2O, you also produce 2 moles of water. Or, put a different way, every time 2 moles of water are produced, that's a little typo there, right? 2 moles of H2O. 1 mole of N2O is produced. It's a 2-to-1 ratio. So that ratio cannot change. It's not like you could ever have 1 mole of N2O and 3 moles of water, or 7 moles of N2O and 2 moles of water. The ratio is given by the balanced equation. It's 1 to 2, or 2 to 1 from the perspective of water. So that means that if 0.2272 moles of N2O are produced, that can be used to determine how much water is produced by using this ratio. Okay? So I'm going to take the 0.2272 moles of N2O. We want to know water. So we're going to pick the second ratio. 2 moles of water for every 1 mole of N2O. That's going to give us the number of moles of water. Okay, so 0.2272, essentially you're just doubling it. And follow along, 0.4544. Moles of water. But we want to know the number of grams. we want to know the mass. Remember, in chemistry, when they say mass, they mean grams. 9 times out of 10 anyways, or if they say grams, they mean mass, okay? So how do we do that? Well, we've got this 18.02, that's the molar mass of water. So you convert the number of moles to the number of grams. So 0.4544 moles of water, and then it's 18.02 grams of water per mole. There we go. This is water. That's why we did the molar masses at the beginning, just to get those numbers done. Times 18.02, and you get 8.19. I guess the number of sig figs is actually 3 because it's 10.0, so 8.19. That's how much water is going to get produced out of the laughing gas. And there you go, 8.19.